No admittance, and they have to wait for the next act to finish before they can come in. We got an agenda. We got a schedule. We got a schedule. Yeah. Excuse me. So you can go after, huh?
So you're saying there's gonna be some hecklers?
Hecklers. Okay. All right. Hello, everyone. Can okay, there we go. So good morning again, and welcome to the general remediation session of the Florida Remediation Conference. My name is Fayaz Lakhwala, and I am with Evonik. I'd like to thanks Gene and the steering committee for giving me this opportunity to moderate this session. We have 4 excellent technical presentations ranging in topics from DNAPL treatment to using sustainable technologies and horizontal wells, and including a case study from a tanker truck rollover. So it'll be a nice blend of different talks. And we'll take questions right after the speakers have concluded their talks. And please, again, use the microphones to ask the questions. And with that, I'd like to introduce Cheryl-Anne Nichols and Ben Alex from Verdantas. And they will be the first presenters talking about the use of biosparging in horizontal wells. So please take away from here.
Good morning. Can you hear me? Okay. Good morning. My name is Cheryl Nichols. I'm with Verdantas. Will be co-presenting with Ben Alex. We are project engineers at Verdantas. Our title of our presentation changed slightly just because it was a very long title on the abstract. So we're going to talk today about overcoming site challenges to successfully reduce petroleum groundwater impacts at a site. To begin, we're going to provide site details about the property and the obstacles that we encountered to prepare our remediation plan for the property. We have a brief discussion of the remedial selection process, which includes evaluation of horizontal wells, a comparison of the costs of horizontal wells with traditional remediation methods, the design and installation of the horizontal well system, as well as the site progress and milestones observed during startup and then after the operation had begun in O&M phase, essentially. We'll provide an overall project schedule of steps that we went through to write the RAP through almost site closure at this point. And then we'll provide conclusions of how the chosen technology of the horizontal network met the challenges at the site. So the site is a former petroleum retail station in Orlando, Florida. The discharge to groundwater was discovered in October of 1991. A subsequent discharge reporting form was filed in October 1991 as well. The site was accepted into the Florida Petroleum Liability Insurance and Restoration Program to essentially fund the remedy at the property. In 2002, the property was purchased by the Florida Hospital, and in 2003, they began redevelopment of the property. The redevelopment included removal of 3 hydraulic airlifts, 3 10,000-gallon gasoline underground storage tanks and 1 550-gallon waste oil underground storage tank. During site assessment, which was performed between 2003 and 2009, off-site migration of the impacted groundwater was discovered under the roadway as well as adjacent properties to the south. The plume did not contain benzene or MTBE. It was essentially TEX and naphthalene. There's no vadose zone contamination observed, and because the source was removed with the site redevelopment, there's no continuing source. 2 RAPs were prepared for the property in 2003 and 2016, which provided or proposed ISCO remediation. However, neither remedy was implemented because of accessibility issues where the groundwater plume is located. So on the map, I just wanted to depict the site is outlined in green in the top left corner of the map. On the southern area of the property, or across the street from the property, there are 5 properties outlined. 3 are red, 2 are green. The 2 green properties are also owned by Florida Hospital. 2 of the properties that are outlined in red are a commercial property and a private residential owner. And initially they were okay with us installing monitoring wells on their properties, but once we got to remediation and large well networks and possibly surface construction, they were no longer interested in us being on their properties. The gated property actually is also owned by the hospital. However, it had accessibility issues as well due to it being a maintenance building. So it's a very busy property. It's also about 80% covered by a building, and then it's also gated. So there's access limitations in getting onto that property. And then the elephant in the room is the 6-lane roadway, which is East Princeton Street. So it's a 6-lane major thoroughfare in Orlando, and it also has 2 median lanes in the middle. So our basically design had to overcome all of the complications presented by these accessibility issues. So one of the remedies that we looked into, due to the size of the plume as well as the accessibility, were horizontal biosparge wells. We knew that we wanted to implement biosparge as the remedy, and so horizontal wells address the accessibility issues that we encountered at the property. So we evaluated traditional wells as well as the vertebrae horizontal nested wells. Traditional wells are normally just one well lateral and constructed within one directional boring. The benefit of the vertebrae wells is that they're individual screens or individual wells that are independently routed back to your compressed air source, so that each well can individually be controlled. So you can target specific areas of your plume, you can target different or set your flow rates, et cetera, to be variable for each individual well versus just sort of, one flow rate for one well, and then, you have pressure and flow losses across that lateral because it can't be controlled. So for this particular project, we chose the vertebrae nested wells because it met the challenges that were presented at this site. All of the wells were installed from one central drilling location. Because each well can be individually controlled, we didn't have flow or pressure loss issues that can sometimes be observed with other traditional horizontal wells. Because everything was initiated at one construction location or one drilling point, it eliminated any surface construction across any of the properties that we were impacting with the design. And then also all of the wellheads were accessible from one central location versus having to access individual well points from different manholes across a property. And because the vertebrae nested wells are more of an innovative way of doing a horizontal biosparge system, we compared the cost of implementation of that plan with what a vertical biosparge system might cost at this particular site, as well as the 2 ISCO RAPs that were prepared for this property in 2013 and 2016. And so essentially the installation and construction were less expensive than a traditional vertical biosparge system would have cost cost because of the size of the plume. We were able to drill from one central location. We didn't have to have access or drill multiple well points across 3 or 4 properties to get the same influence from the biosparge wells. And the ISCA was also an expensive or more expensive option just due to the size of the plume. So between the amount of material that was necessary to inject plus the actual cost to perform the injection, the horizontal biosparge system utilizing the vertebrae wells was the preferred choice. Additionally, you can see operations and maintenance were on par with what a traditional vertical biosparge system would have cost because it's the same equipment, it's the same operations and maintenance as far as that is concerned. So the design specifications for our particular property included submitting a RAP to Orange County Environmental Protection Division in July of 2018. The site specifications include a 16,600 square foot plume that's about 350 feet in length. Because it's a biosparge system, the flow rate was set to 3 CFM and 8 PSI per well. And we estimated a radius of influence of about 20 feet based on historical pilot testing that was completed at the property. The design included 2 directional laterals that would be constructed across 3 properties. The laterals, each lateral contained 8 well lengths, and then for a total of 16 biosparge wells. The laterals, each individual lateral was constructed of 1/2-inch HDPE conveyance piping that was connected to a 1/2-inch diameter 0.06-inch slot screen. The screen lengths were each 10 feet, and then the conveyance pipe between each screen length was 15 feet. And then the original RAP actually included a lateral that was supposed to go under East Princeton Street, but we couldn't get the well construction permitted with the city. They wanted no construction in the road, so that lateral was removed from the design. Probe Domain completed the directional drilling. The target depth for the laterals was 30 feet below grade, which is represented by the green triangles on the figure. To get to 30 feet, the drilling was initiated 125 feet west of that target depth, and it was initiated at a 15-degree angle to get to 30 feet. Once the drilling got to 30 feet, it was leveled off, and it continued under the neighboring 2 properties at that 30-foot depth. The boring was blind drilled, meaning it did not daylight on the opposite end, and a beacon was used to track the end of the drilling probe across the properties to make sure that we were sending the wells in the correct design location. The laterals, the vertebrae laterals, were advanced in 2 sleeves in each of those individual borings. Once the laterals were positioned, the sleeves were removed, which allowed native soil to collapse around the well screens and the piping, setting the wells in place. And then finally, the laterals were pressure tested to ensure that the screens were not blocked by soil or any of the drilling fluids, and that the pipes themselves were not damaged during construction. So then surface construction was completed by Petrotech. The construction at surface is similar to what would be performed for a traditional air sparge or biosparge system, where the pipes were buried in a shallow trench and then directed to the equipment compound to be connected to equipment. So no real challenges were presented by any of the surface construction. That was pretty straightforward. But it was simplified by the fact that we just had one trench that ran all of the laterals back to the equipment compound. And so now Ben Alex is going to take over to talk about the startup procedures and findings.
Thank you, Cheryl. Good morning. My name is Ben Alex, and I am the project manager, Verdantas project manager, working in conjunction with Orange County Environmental Protection Division to bring about site closure for this project. Cheryl had mentioned at one time the plume was over 16,000 square feet, 350 feet in length. It had migrated off-site, was beneath a major arterial road, affecting multiple down gradient properties. For O&M purposes, we considered this site from the standpoint of non-right-of-way monitoring wells and right-of-way monitoring wells. Pictured here are the four key monitoring wells, four key monitoring wells. This well here, 39, is a right-of-way monitoring well. The next three wells, southern wells, are non-right-of-way monitoring wells, 18, 32, and 35. For this presentation, I like to consider these wells installed along what I'm calling the longitudinal axis of this plume. Note the plume area, GCTL and NADC. Note the location of these two wells within between these two laterals, 18 just north of the northernmost lateral and 39 just due north of that in the right-of-way of Princeton Street. Average depth of groundwater out here was 11.5 feet. Typical well construction was 18 feet, 1-inch diameter with 10 feet of screen. The deep well was 1-inch diameter, 40 feet with 5 feet of screen. We were required to sample on an annual basis 20 wells, the majority of them in the right-of-way, inclusive of all four key monitoring wells, and on a quarterly basis, 6 monitoring wells, 3 of which were the lower 3 key monitoring wells outside of the road right-of-way. So at system startup and all throughout active remediation, we operated a Reachla DLR 150 rotary claw compressor equipped with a 15 horsepower motor. That unit was able to deliver air in excess of design specs. We typically saw flow rates from 3.5 to 4 SCFM at pressures ranging from 12 to 20 PSI. That particular unit consumed roughly 6,400 kilowatt hours a month at an average average monthly cost of $850. Now, looking at this dissolved oxygen graph of key non-right-of-way monitoring wells, 35 up top, 32 in the middle, and 18 in lime green down here at the bottom. The graph implies a good distribution of air all throughout the plume area. If you recall, those particular wells are along the what I'm calling the longitudinal axis of the plume. At startup, DO concentrations were elevated, and they maintained elevated concentrations all throughout active remediation. Dissolved oxygen being a critical metric to track in order to evaluate the progress or the successfulness of your project. Another parameter to track is contaminant reductions. At this site, and even at startup and even before, it was heavily contaminated with TEX compounds. They were routine in all four key monitoring wells. They were above NADC values. Naphthalene in all four key monitoring wells was above GCTL values. As Cheryl said, there was no benzene, MTBE, lead, or TRPH issues to deal with out here. TEX and naphthalene. So at startup, in all four key monitoring wells, we saw a sharp decline in TEX concentrations. We saw reductions over 99%. We saw reductions in naphthalene concentrations of over 90% in 3 of the key monitoring wells, the outlier being 18, where we had a increase in concentrations during the first year of operation, and subsequently in year 2 of operation, those concentrations reduced by over 99%. The system ran for another 2 months, and it was then determined to transition the site from active remediation to well abandonment and PARM sampling. The construction, the contaminant construction reduction for all of these wells is pretty similar in that the first year of operation we had these large drops in contaminant concentrations, almost to GCTL values, actually at GCTL values. During the second year of operations, those values were held, and then after another 6 months of operation, it was determined to decommission the system and move to well abandonment and PARM sampling. So a typical project schedule looks like in 2018, the RAP was eventually approved. In fourth quarter of 2021, we did startup. Again, the system ran for 2.5 years. In June of 2024, we did system decommission. And then we just recently have received a purchase order to abandon all right-of-way monitoring wells and to conduct 4 quarters of PARM groundwater sampling. The reason why the time delay between 18 and 21, primarily, well, we were able to accomplish permitting, system installation, and baseline groundwater sampling, but as we all know, during this time frame, we were also dealing with COVID. So that was a big part of the time delay. In conclusion, because of the size of the plume, its location beneath a major roadway, its impact on downstream property owners, who quite frankly were at this time pretty much done with allowing site access. They were done with vertical well installations on their property, and they wanted nothing to do with any more trenching of the like. The use of the nested horizontal well system enabled us to overcome and circumvent those challenges. The system was installed comparatively at lower costs, and it effectively reduced contaminant concentrations below treatment goals on schedule. Now, as I mentioned, we have one remaining purchase order, and that is for the abandonment of right-of-way monitoring wells and the conducting PARM groundwater sampling from 6 non-right-of-way monitoring wells. There are, we're going to abandon 13 wells in the right-of-way. 3 of those wells have one clean data point, so we're going to sample those wells, abandon them, and at the same time conduct the first quarter of PARM sampling. If after 1 year of PARM sampling, those wells maintain their GCTL compliance and the wells sampled in the right-of-way are clean, the site should be eligible for SRCO, no further actions. If, however, the PARM wells maintain their GCTL compliance, but say one of those wells in the right-of-way comes back hot, then it's quite likely the site could be eligible for a risk management option level 2, no further action with institutional controls. The current purchase order that we have ends in March of 2026, and by that time we hope the project is completely finished. In closing, I'd like to thank the Orange County Environmental Protection Division, specifically Jim Russell and Brian Nicholson, for their assistance and guidance. NRX, Petrotech, Probe Domain, and ESD Waste to Water. That concludes the presentation. If there's any questions, please ask.
Quick question. Based on your plume diagram and your statement that one of the advantages was to address the no access to the roadway, I didn't see any data for GPW 14 and 15. What was the approach with the concentrations underneath the road, and what is the type of closure that you're pursuing for that if it was not addressed?
Those wells were sampled annually, so I don't have a whole bunch of data points to show the concentrations in those wells. I didn't quite understand the second part of your question.
If you did have residual contamination underneath the roadway because you didn't have access to install the horizontal well to that area, if there's any remaining contamination underneath the roadway, what was your closure strategy for the groundwater quality remaining there, if that's the case?
The closure strategy, that's what you were talking about.
Yeah, the closure strategy is if the non-right-of-way monitoring wells maintain GCTL compliance and those right-of-way wells come back clean, then it should be an SRCO, no further action. If those wells in the right-of-way are going to get sampled and they're going to get abandoned. We're done with the right-of-way. So if those wells come back hot, they're hot. And if the PARM wells maintain GCOTL compliance, then we're going to have to shoot for some other type of closure other than a straight-up SRCO, no further action. I mean, the wells will be abandoned. That's what they want to do. That's what's going to happen.
Can you discuss any concerns you had with vapor intrusion and how you were monitoring for that and any structures that run above that?
Yeah. So we didn't really perform any vapor intrusion studies or anything of that nature. Based on the depth of contamination and then the amount of vadozone between, I think Ben had mentioned the depth of groundwater was like 12 feet, so there was a large vadozone above the groundwater table, so that we didn't anticipate any vapor intrusion issues. And it was also low-flow biosparging, so during startup, the area was monitored with like an OVA just for any fugitive emissions that may have been generated by the biosparge system.
In the monitoring wells?
At surface, in the buildings, different areas of the property, that closer to where the well laterals were. One of the residential property owner had kind of a lot of plants and stuff in his yard, so we were kind of, measuring at ground level and chest level around his property as well, just to make sure we weren't really generating anything.
The issue for monitoring within the unsaturated zone when you initiate a biosparging, just to ensure that you don't have a potential cross-contamination to the unsaturated soil. So it will be beneficial to have that documentation. And back to your answer to the first question, I did not see any data for GPW 14 and 15 indicating that they were below the groundwater CTL, but that might be the case, but you didn't indicate it during your presentation.
Thanks very much for the presentation. Actually, I think to follow up on that question, was there consideration for monitoring under the roadway if you're not using the MOU process to maybe do horizontal groundwater sampling to get further into the right-of-way or figure out where that plan is? And would that be a consideration in the future?
So part of the reason why the wells are getting abandoned is because the city does not want the wells in the right-of-way anymore. They're getting public complaints about the lids, et cetera. The wells are vertical. We had a horizontal lateral actually planned for design, and we could not get it permitted by the city. They did not want us drilling anything under that roadway. So monitoring well, remediation well, anything. It was basically anything that was going to go under the road. They just said, no, thank you.
So I guess the question is, it's not a DOT road, is it? Or is that a city road?
Orlando.
City of Orlando, okay. So you can't use really the MOU to close that area, like contaminations under the soil, under the roadways, you can't.
We definitely received, we had to sample the wells on an annual basis, so we did receive permits to do so, and we closed lanes and to complete that effort.
We have time for one more question.
Hey, I'm sorry, I'm with the city of Orlando, and the reason that we don't allow people to do things underneath the road is it's all clay pipes. All of our wastewater system runs through there. So the possibility of you guys coming in and doing something horizontal through the roadway is going to potentially damage the integrity of our pipes. So obviously there's a problem with that. And we also have had some, several lawsuits because of people's cars being damaged and stuff. So I apologize for that. We're not trying to impede any of your work out there.
No, you're fine. Thank you.
One more quick question, if you don't mind.
Yes.
What does the abandonment of these horizontal systems look like?
I'm sorry?
What is the abandonment of the horizontals?
The abandonment?
Yeah. What does that look like?
We-
Do they stay
we
in
don't-
place forever?
no.
Do you pull them? Do you fill it with grout? What does that look like?
We're abandoning the monitoring wells. We're not doing anything right now with the horizontal wells. We're abandoning monitoring wells in the right-of-way and off-site properties.
Okay.
Right now, they're just being left in place.
Thank you.
Thank you again. Okay, our next speaker is Michael Spievack. He's with Langan Engineering, and his presentation is going to be on a sustainable use of a bioelectrochemical system to remediate petroleum impacts. So, Michael, take it over.
Good morning and thank you. Very excited to be here today to talk about a sustainable remediation technology. Not something we often hear about, but it's working. It's an option for bioremediation, and it really can work for clients with minimally invasive work. Before I start, I do want to thank our partners with Advanced Environmental Technologies. They cannot be here today, but they helped develop the technology, and they were part of preparing this presentation, as well as my colleagues at Langan, Aruna Budram, Stephen Sherman, and Stu Abrams. So let's talk about the site first before we get into the remediation and why we chose to go this route. As part of a grant program, the city received funding to upgrade their city-owned facilities. This is a, that was the wrong one. But this is currently their fleet maintenance operations facility right here. It's very small, and they have very little room on the site for any type of interferences at this time. But more importantly, the future use of the site, it's going to be their new city park. So once they relocate their fleet facilities, they're going to build a brand new city park, the largest in the city. So let's talk about the site history, because there's a lot going on at this site, and you may recognize part of this from the PFAS forum. I did say I was going to be back possibly in a couple of years to talk about this, and thank you, Gene, for having me back. But the site started off as former agricultural land, and this was very important in our remediation technology evaluation, and I'll tell you why shortly. There was also equipment and chemical storage facilities for all of the city's parks and fields. Their chemicals were stored at this facility. In addition to that, fire station number 9, it got moved. It literally did just get moved, actually. And the fleet fueling and maintenance facility, which I'll be talking about today. So as part of the grant funding program, we evaluated the site history. We kind of did a phase 1, phase 2, but more streamlined. We did find the AFFF discharge that I spoke about at the PFAS forum. We did find a small arsenic plume, very low level, on the southern portion of the site, associated with either the agricultural use or chemical storage. Also, there was a small oil discharge in the maintenance bays. Nothing impacting groundwater. Everything was capped, so the city and the county agreed to allow this to be left in place until demolition. And then, of course, the petroleum discharge, which is right about here. This is the fleet's, this is their pumps for their fleet vehicles, and the tank is right about here for all their fleet fueling operations. So we went through a site assessment on this. The source of the discharge was a 1987 petroleum discharge. The city put this into the brownfields program for voluntary cleanup tax credits. But so a lot of this work was done under that program. We have a plume right about here, and it's a very small plume, but it's centered right on the Vita route. All the electrical go into the maintenance bays. It's in a very inhospitable area for construction and trenching. But our contaminants of concern, your typical petroleum contaminants of concern, BTEX, isopropylbenzene, cumene, and PAHs, mostly 1 and 2 methyl naphthalenes. It is noteworthy that there's really no discernible groundwater flow at this site. I mean, occasionally we see something to the southeast, but it's very rare. There's also very little vadose, the groundwater is 2 to 4 feet. We found no soil impacts in the vadose at the site, so the mass was definitely submerged or right on top of the tanks where we could not reach it. And I will touch more on that. More importantly, and I overlaid the future use of the site onto our area of concern. This is proposed to be the children's play area for the future park, directly connected to a reading room in their new community library. So this was making the city a little nervous. They wanted to get a jump start on remediation so that they weren't having to deal with this during construction. This is one of the main reasons we were out there. So a lot of folks might be familiar with this triangle if you've done remediation. You know, everyone wants good remediation, everyone wants it fast, especially those who work with developers. But very rarely are we able to go the cheap route unless it's bioremediation. We were fortunate in this case when discussing our remediation goals with the city. Primarily, they wanted to remediate the BTEX pH compounds, cumene as well. It was a goal to remediate, but there was consideration of leaving some of that in place. Most importantly, they could not afford us to interfere with their fleet operations. That really limited the technologies we could use. And, which is very, very nice, we had at least a 5-year timeline to get this done. Recently, it's stretched out to 6 due to construction delays. So we had plenty of options, and we were able to work in the cheap and good range on our triangle. So we evaluated various technologies. I want to mention Sparging first. We didn't do any kind of studies for Sparging because that was immediately ruled out just because of the need for trenching and placement of an equipment trailer. So we looked at chemical oxidation. We did a soil oxidant demand test for alkaline activated persulfate. We were near the tanks. We wanted something low impact to the tanks. Unfortunately, what we felt would be safe to do near a tank field was not effective on the naphthalene compounds. More importantly, and this goes back to the historical use of the site, the chemical oxidation in our treatability study, which was done at our lab at the New Jersey Institute of Technology, it mobilized metals. We already knew there was arsenic in the soil from the agricultural use. We did not want to mobilize any more arsenic, aluminum, or lead, all of which were mobilized during the treatability study. So we started to look at more bioremediation options. We had the time to do bioremediation. We wanted to keep it on the lower side of the budget since we are using taxpayer dollars. And we reached out to AET, Advanced Environmental Technologies, and about their e-redox technology. And I'll go into detail what this technology is, but they did a bench scale study at their facility for us and achieved 99% reduction in all contaminants of concern during the study, which just blew our minds. We were, of course, this is a new innovative technology. We were a little skeptical, but I'm here talking about it, which means it's been going well, right? So what is e-redox? What is this sustainable technology? It's essentially a way to supercharge bioremediation. It is a patented technology by AET here in the US, China, and Australia. And there's both an oxidation and a reduction version. I'll tell you what the reduction version is, but we're going to focus on the oxidation version since this was aerobic bioremediation. But as is the case with all aerobic technology, is pretty good for all your petroleum compounds that you'll commonly see. So what is e-redox? Specifically, what is the oxidative version? Well, it's a cathode and an anode. The words got cut off there somehow. We've essentially put a battery in the well that both charges and discharges at the same time. The e-redox oxidative version, we're generating a low voltage electron current. So you got to go back to your biochemistry and your back to school days. And bioremediation, it stalls when there's excess electrons, at least the aerobic version. So if there's nowhere for those electrons to go, if there's no electron acceptor, you're not going to be able to remediate the site using a bioremediation process. These units solve that problem with the anode and the cathode. I'll tell you more specifically on that in a moment, but all we have to do with these units is slide them down a remedial well. That's it. That was the entire construction process. We drilled some wells and we put the units in them, 2-inch wells. Very simple. The reductive version, it's a bit more complicated. It's more of an array. You have to create a reductive field. You do actually have to add electricity to that, but the electricity, it's low voltage. You can do it with a solar panel. You can do it with a battery. You can do it with a wind turbine. So very sustainable, low impact remediation. And with bioremediation, always a little less expensive, but it does take a little bit longer. So here are the mechanisms of e-redox. So as I stated, we're finding we needed to provide an electron acceptor. Usually, if you do something like air sparging, the electron acceptor is the oxygen or biosparging. In this case, there was some oxygen in our groundwater, not too much, but with the relatively low, high groundwater table and the very small area of this plume, this was a very good option. The anode right here, this sits below the water table. You know, just like any battery where you charge it, you discharge it, you know, anode, this is where all the oxidation's taking place. The electrons are being transferred to a cathode that straddles the air-water interface. I'll show you what those look like in a minute. And that cathode ultimately transfers these spare electrons to atmospheric oxygen as the terminal electron acceptor. This connection right here, we're actually able to measure if bioremediation is occurring simply by measuring the voltage from each of these units. You know, so a little bit more on this, you know, we have our bacteria here, they're stripping electrons for lack of a better term, and those electrons are being transferred to the anode, being transferred to the cathode, which is being transferred to atmospheric oxygen. That's the simple version. Folks a lot smarter than me came up with this though. So since this was a new sustainable technology, you know, we wanted to test this out. We had the time to do a pilot study. We went to our hottest source well. There's two source wells, MW13 and MW2. I'll show you the data on both of those in a minute. But let's start focus on MW13 for a little while. So MW13 is right here. And these are the two e-redox wells and units that we installed. One 7 feet away, one 10 feet away. You can have a rather large radius of influence in more conductive environments, but because we had not tested this before, it has not been used in the Southeast previously. It's only been done 12 times in the United States. We were very conservative in our estimates, 7 feet here and 10 feet here for our pilot test wells. Again, here's what the unit looks like, a schematic. The anode sits below the water table, the cathode sits above it. And you have these two leads right here, that one leading from the cathode, one leading from the anode, that, you know, we test the voltage between those two, and that's how we know if the units are working. So again, the operation and maintenance, this is an example of just measuring the voltage in an e-redox unit. This is an example of what the leads look like. We only had one O&M problem in the past 2 years with the corrosion of a couple of the leads, so these units are pretty durable. But our monthly O&M simply takes about 10 minutes at each unit, measuring the voltage, inspecting the units, checking for biofouling, and making sure they're in good condition. There's quarterly groundwater monitoring, of course, but what we're looking for on each O&M visit is a voltage less than 10 millivolts. That tells us their bioremediation is not ongoing at the time. There's no electron transfer happening. So here's the data for the pilot study. You know, up front, cumene, isopropyl benzene was around 150, and naphthalines were around 80. Almost immediately after installing the wells, the e-redox units, concentrations dropped. And over time, though, we started to see a bit of an increase. This was part of testing out these units. And what we discovered, along with the equipment manufacturer, is that we need to change our cathodes out. They tend to biofoul and get used up rather quickly in the source area. So we came up with about a quarterly O&M schedule to replace the cathodes on each unit. Specifically in the source area, the cathodes do last longer outside the source area in the perimeter. I would say down gradient wells, for lack of a better term. But you know, we started this cathode replacement cycle, and these were the concentrations just before we replaced the cathode. These were the concentrations just after. And as you can see, by doing so, our naphthalines were already reaching GCTL in MW13 at the end of our pilot study. Cumene did stick around a little longer. Those are different degraders. We weren't expecting them to disappear at the same time. But this was enough information for us to say, you know what, this is a good technology, this has potential, and the city was on board to try something sustainable. A little bit more on the pilot study. These are the voltages. I'll jump backwards real quick, but if you want to focus on the dip in November, well, it's not going backwards, but that coincides where we had to change the cathode. Those were low voltages that we were measuring during our O&M visits that clued us in to us having to change the cathodes out or do something differently. And as soon as we did change those cathodes out, the voltages went back up and our concentrations in our MW13 went down. So with all this information, we went in front of the city and the city council, and we got approval to go to full-scale implementation by installing 5 more units. So overall, we have 7 units installed with radius influence of about 10 feet, 7 feet in the source area. And these are the units. These are the units we installed. The feather duster looking thing, that's the cathode. And the anode is inside this PVT tubing. It's slotted tubing to allow water to be in contact with the anodes. So we got a lot of data here. I already showed you this pilot test data, but what we added here is the voltages. So focus on the dotted lines, and as you will see, as the voltages are going up, here, our concentrations are usually going down. So we started the full-scale operation in about the middle of 2022. And we suddenly saw our concentrations going up after a little while, which threw us for a loop because it did not match the pilot study. We started taking some additional groundwater samples to evaluate what was happening, and we started to realize that our nutrients in the groundwater were depleting at a much faster rate than we expected. So we entered into a UIC. We had to get a UIC permit. We had to submit a RAT mod and get a UIC permit to inject the specific nutrients that we felt were best for the site. Now, these nutrients, they did not have an innovative technology approval, so we kind of had to start from scratch here. And unfortunately, the process to get that approval took about 6 months, so we did have to pause remediation. But we eventually got approval to inject gravity feed, really, 26 pounds of diammonium phosphate and 3 pounds of potassium chloride every quarter. We just gravity feed these into each of the E-redox wells. The process for doing so, we had to send all these products to the labs, get leachability testing for both the potential impurities as well as the raw materials. It was an interesting conversation with the lab, asking them to test pure potassium chloride, but they made it happen for us, and we eventually got our permit. And that's this line right here. So you can kind of look at the overall trends in the background, but if you want to focus on the right side of this graph, these are the concentrations in MW13. Immediately after injecting, concentrations started to plummet. Now you do see them rising right about here. Unfortunately, we then hit the end of our contract, and we had to wait for our contract renewal before we could do more work. But so we did get a little bit of spike because we had to stop the remediation temporarily. But only in MW13 did we see that spike. And this was actually, in my opinion, a very good delay, because what we're seeing here, this is MW2, our other source wells. Same trends in groundwater data as MW13. Concentrations went up relatively similar proportions as they did in MW13. But as soon as we started doing our nutrient injections, concentrations have continually declined, and they've stayed declined. Now, I've added phosphorus to this graph instead of the voltages, because that was pretty much a good indicator nutrient for us to show that as our nutrient levels were going back up, our bioremediation did continue, and MW2 is now below the GCTLs, leaving just MW13 as a well of concern. I do want to touch on the water table elevations and potential mass transfer. This was a big concern for us because although we did not have soil impacts in our area of remediation, we did suspect there were some impacts in the soils on top of the tanks that were causing these issues. If you look at these purple lines, which is now water table elevation, as water table elevation was rising, we saw an increase in concentrations shortly after. That was basically during the wet season, October. This is MW13. You see that trend. It's possible we're seeing a little bit of mass transfer at this point. But if you, again, look at MW2, which is closer to the tanks, concentrations have remained below CTL, and water tables are rising. We suspect the mass transfer that was going to occur has already completed, but we're going to be keeping an eye, and we're going to be focusing our remediation on MW13. But just for a quick comparison, the plume in 2021, more significant than the plume in 2024. So we've significantly reduced the size of this plume, no trenching, no equipment, very minimal O&M, and very minimal interference with the facility. I've mentioned this is a sustainable technology. We estimated the carbon footprint of this technology specifically for this site. With a typical air sparge SVE system, we estimate the carbon would have been over 6,000 metric tons generated from the remediation. Chemical oxidation, great option, 24 metric tons, but the e-redox, we estimate only about 1 metric ton of carbon being generated, mostly from transportation of the units going to and from the site for O&M. So very, very sustainable option. But we did have some conclusions, and we did learn some things. You know, we can't see a sustained decline in our contaminant concentrations using a sustainable bioremedial process, but it's anything innovative and new, especially anything biological, you definitely need more robust groundwater monitoring. We wish we had picked up the nutrient deficiency a little bit earlier, but we had paused the groundwater monitoring during the UIC permitting, and we tried to limit what we were sampling for to minimize costs on a monthly and quarterly basis, because this was taxpayer dollars. Additionally, you know, we need to understand the biochemical system that's there natively. We took some time to do so, both before we started this and afterwards, by making sure we had the proper degraders on site. But, you know, what everyone needs to remember is innovation is going to provide challenges, and we're going to be seeing that in the coming years as we move into PFAS remediation. We're going to be dealing with a lot of new innovative technologies that are going to require and are going to provide us a lot of new challenges in the remediation world. Thank you. Any questions?
I have a question. Is the cathode regenerative?
Could you use the microphone?
No. Can you regenerate the cathode?
She asked if we can regenerate the cathode, and we do. So each time we remove the cathodes, we do send them back to Advanced Environmental Technologies, and they do recycle them and reuse them. Yes, it does. It increases our sustainability. Thank you.
Thank you very much for this presentation.
Yes.
This is an interesting approach. You didn't have to seed the aquifer or anything beforehand, did you? Or did you do any testing of which bacteria are actually present?
We did send samples to Microbial Insights, and they did evaluate that we had the correct degraders present. We did that again about halfway through the project just to see if the populations were increasing. And we did note that in one of the wells, a little bit outside the source area, where there was a little more residual nutrients, the degraders were a bit higher. So we actually saw, we literally would have been able to see this working either through O&M or through lab testing.
Great presentation. Question. You mentioned that you had isopropyl benzene or cumene at like 150. Normally, we see like 1,2,4 and 1,3,5 trimethylbenzene when the isopropyl benzene is pretty high. Did you notice that as well? Or did you test for that?
We did test for those. We did not identify 1,3,5 or 1,2,4 trimethylbenzene.
Really? Okay. Great. Thank you.
Hey, yeah, good presentation.
Thank you.
Quick question. On the UIC permitting that you had to get, did the state require you to sample for additional UIC parameters based on that? And what kind of results did you see from that?
Yeah, so we did run our raw materials through the lab. That was really interesting, trying to get down to the GCTL with potassium chloride to test for those impurities. But we added arsenic, iron, quite a few other metals to our sampling protocols. We've done a pretty good job. I believe we're within our baseline concentrations for all of our injectable parameters.
What was your frequency of dosage for your nutrients and also your concentrations?
Our frequency of dosing is quarterly.
I'm sorry?
We dose quarterly. We sample, then we dose, just to make sure that we do actually need to do that to save money for the city. You asked for what the concentrations were?
Yes.
I don't specifically have those handy, but about 12 gallons of water, 26 pounds of diammonium phosphate, and I think 3 pounds of potassium chloride, which honestly, we just bought that at Home Depot. More than salt.
Thank you.
Hey, Michael. Yeah, very good presentation. I like the, innovative technologies. However, how do you interpret the 2021 natural, decreasing concentration before you placing the cathode?
So before we place the cathode, how do we integrate the? I didn't get that part.
Before your pilot test, the concentration decreased from the peak almost to after your treatment.
Yeah. So the decrease, I mean, we attribute that to the units. The increase, probably a couple things going on. One, the cathodes were wearing, the nutrients were starting to be depleted, and we were seeing some mass transfer at that time.
Yeah.
Okay, I guess we are running out of time, so thank you, Mike. Okay, our next presenter is Derek Pizarro. He's a senior geologist and product manager with ASD Environmental. And he's going to talk about a case study related to a gasoline tanker truck rollover and what they did to implement the remediation there. Okay, Derek?
Thank you, Fayaz. If you're filling out your bingo cards, you might have missed Gloria Gaynor. I think I heard Katrina and the Waves and Taylor Swift. So if you have bingo at this point, go see Gene. I don't know what prize you're going to get, but I'll do the best to keep up with the party going on next door. Good morning, everyone. Derek Pizarro, AST Environmental. I'm one of 6 principals with our company. I manage a lot of our East Coast design and operations. So as was mentioned, I'm going to talk about a gasoline tanker truck rollover that we use something called qHRSC, which we'll get into, and then also an activated carbon-based injectate to remediate it. One of the overarching comments I'm going to give at the outset here that's going to apply to a lot of the slides is we are looking for ways to optimize every remedial site, right? We're looking for ways to add sustainability, to decrease time on site, to add things that we didn't think about even 5-10 years ago. And a lot of that starts at the outset, right? So I'm going to focus the first half of the presentation on the qHRSC, which gets us to a cogent, applicable, optimized both for cost and remediation design. All right, so what types of characterizations? I'm going to use the box concept, right? I've heard backpack, I've heard pot, I've heard others. I'm going to use a box, right? So most of us in this room are probably familiar with conceptual site modeling. CSMs, obviously, that's everything you currently know headed into a site, right? You put it in there, you develop your conceptual site model, you look at what your priorities are, what your constraints are, what your regulatory criteria are. From there, you have to start drilling down. Now, several, if not many of you in this room have probably used HRSC, high resolution site characterization, right? It's a means to look at the site without having to take a broad array of wet chemistry samples for soil and groundwater. The advantages to that are it's rapid. The disadvantages to that is you do not have a real sample associated with it that's a true representation, right? It's an interpretation of an electronic output signal. So I like to say now we're inside that box, which is our CSM. We're going to find a corner of that box or a little piece or parcel within that box that we have to look at, right? HRSC gets us into the box. The next sub-level of that is where we have to start looking at physical soil and groundwater samples, right? This is a targeted area that we've identified at a site which needs active or passive, but some sort of immediate remedy or resolution to it, right? And to understand what we have going on in that subsector of this box we're talking about, we have to go in and take physical samples, right? So how do we know where to do that and how to do that? Well, the previous methodologies on that slide get us to that, okay? And so qHRSC is actually a way to twin the HRSC component with taking qualitative data and adding quantitative data to it. And so that gives us a remediation design focus, right, where we can design stoichiometrically for your site based upon those actual soil and groundwater samples. Now, we're still using, as we build the model, those qHRSC data, because we want to create a 3D model. I think a lot of us in this room are using 3D modeling for a lot of our clients, stakeholders, site owners, right? It's a great visualization, especially for people that may get mired down in what we actually do as practitioners, right, or they don't understand all the regulatory requirements, right? It's something that, you know, John Q. Public, right, Jane Smith can understand, right, a model. They see its visualization. So putting things into this model is something that's very important from the start. The best part about adding the quantitative data to this qualitative data set is you end up with actionable data, right? So this comes back to stoichiometric calculations. There was a question about nutrients in the last presentation, right? A question about what products are you going to use. Without that wet chemistry, being able to take concise calculations, you can't evaluate apples to apples, different chemistries, right? You're not guessing, right? Actionable data lets us choose very specifically our alternatives as we move through a site. The last part about qHRSC, which I think is the most important, is you have to set expectations. If you have a terminal site, right, you're never going to get in any reasonable lifetime to a residential property, right? But you may have different properties that are, you know, corner gas station, a dry cleaners, different levels of impact and expectations from the stakeholders and regulatory bodies that you're working with. I think setting expectations is the best part about using qHRSC, is you fully understand both laterally and vertically in the subsurface what you're dealing with, and you can make rational, cogent, complete decisions as you move through it. So we've talked about this. I always go back to the bullet point, what's the story, right? So being a geologist, right, the story of the site, right, how did this site come to be, right? Why do I have fine to medium sands here? Do I have a clay lens here? Do I have a stringer here? What am I dealing with here? But you also have to look at the anthropogenic impacts to that site. How did I get to these issues I'm dealing with now? Because if we don't fully understand them and we're guessing, we say, well, generally, if this type of, you know, groundwater velocity and this type of geology, I expect this to happen. Okay, that's a good place to start, but until you fully rationalize why you made that decision, it's not a good way to guess, right? We don't want to guess. Again, we want to come back to what is the reality, what is the actual story for this site, right? And in any story, you're going to identify questions. In our world, that's data gaps. So the best way to think about this sub-level, right, to your CSM, this drilling down into this qHRSC, again, marrying up qualitative and quantitative data, is to identify data gaps, right? You have to complete the story to get to your end, right, to get your happy ending. I'm going to give you a brief example here. This is a site in the southeast. This is not the case study I'm going to show you at the end of this, but this is just an example of a gas station site. And what we're dealing with here is they did some removal action in the mid to late 90s. They've got a lot of groundwater wells at the site that they installed previously. They have limited soil data, right? We're really just going off of what they've been doing for historical monitoring. They still have a problem. The plume there is identified on this map. So to get out of this and to not have to put in a remediation system, the consultant here asked us to take a look at the site. And so on this map, you see these 31 high-density soil borings that we took. We're also twinning them with existing monitoring wells, and in some cases, we're taking discrete or temporary or screen point sampling, groundwater samples at some of these locations to twin with the soil data. Again, looking at the soil and groundwater components in each subsection of this site is going to get us to a design that's going to create actionable data, and then we're going to be able to move forward with an injection in this case that gets us to our targeted goals. I would point out there at the end, there's varying degrees of laboratory support. One of the ones that we use is out of Denver. This is provided by one of the technologies that we do represent, which is called Trap and Treat. They represent a performance laboratory in Denver, Colorado, which is USDA certified, so you can send samples here in the southeast to them, and they will run them pro bono because they believe that knowing quantitative data is important to deploying their products, and if it doesn't fit, they want you to look at something else. So they offer this through their provider network to run those samples for free. So all those samples you saw on the previous slide, they were run for this site, right? And then we're going to incorporate those into a 3D model, right? We've talked about a few of these things on this slide before, but I'm going to hint at, again, We did not use qHRSC at this example I'm giving you here because the size of the site. If we had a much larger site, we probably would have at the outset included some high resolution site characterization here to get us within that box, right? But on that previous slide, you saw it was a pretty well contained, though highly impacted plume. We elected not to go with the qHRSC, and we went right to the actual RDC data. So again, a nice model here, and you can see the reason we start, and we like the idea of a 3D model at the outset, is once we start injections, and so on this example here, every single orange disc there is a vertical injection, and you can see the plume represented behind it, just the low level, I think that's a benzene plume represented in that example there, just the low level blue plume peeking out from the cross sections there. You can see the areas you've targeted. And it's also important for injection contractors like myself, you can see the gaps that sometimes if you get refusal or you get back pressure or something, or you have to skip an interval for some reason, you now have a visual way to go back and say, okay, should I revisit that interval? Should I create an additional boring next to it to account for that skip or that miss, right? It helps everybody involved with the project understand what happened, likely why it's happening. In a lot of cases, we can determine that. And what should we be doing moving forward even before we move off the site, right? This data, the way we do it, it's installed real time in the field. So our consultants, our clients, our stakeholders can make a decision real time before anybody's left the site and says, oh, we got to go back and do something else. Again, it creates easy communication for everybody involved. So here's this same example, again, going back to this gas station. When we received the initial CSM, we came up with a preliminary design, which you see on the left here, and we identified 4 specific areas that would get different targeted loadings of a product called BOSS 200, which is an activated carbon-based platform for petroleum hydrocarbon remediation. That's the product you'll see deployed in the case study. After we completed the RDC, you'll see on the right, we've now subdivided this into 8 unique areas. So this isn't just a chemistry optimization, it's also a cost optimization. You're now rationalizing to your client why I'm either doing more or doing less, not just laterally, but also vertically in the subsurface. That's the kind of resolution this program gives you, is you can change the mix, injectate design, not just by area, but also by depth. All right, so let's get to that case study. So this is a US 23, it's a state route. There's a tanker truck that rolled over there. You can see identified in the source area. We've got groundwater moving to the southeast at this location. Approximately 4,000 gallons of gasoline were released. There was a relatively quick environmental response cleanup. A lot of it was excavation. They removed the soil. Within 24 months, they'd gone out. They'd installed 14 groundwater monitoring wells. They notified the state of expanding plume conditions. It's now leaving the corridor of the US highway here. And you can see from this aerial that we have pretty much surrounding us, even though this is pretty rural, there are some farms and homes in the vicinity. So we definitely have some sensitive receptors, and not in this picture here, there's also a water body to the east, freshwater water body to the east of this. Challenges and objectives. I always start with safety, access, and utilities, right? So I included a picture there of a pre-dig. But that was one of the biggest challenges we had at this site was, one, while we could have access to the right-of-way, while we could, and it was permissible for us to inject on an angle underneath the roadway in this case, we did get a permit for that. We still have to deal with, as with a lot of roads, especially in rural America, those are also utility corridors, right? So here we had, everything was buried, right? So we're dealing with a lot of underground utilities within this corridor. As you saw, if I can go back, as you saw here, right, you can see the plume migrating with the highway. That's really not the highway, right? That's really using the utility corridors for transmissivity here of the contaminant. So we're dealing with issues there as well. So we have a lot of mark out. We have a lot of soft dig involved at this site. We're also dealing with, as you saw from that heat map of benzene, we're dealing with significant saturation. We're talking levels greater than not just 1 ppm, but greater than 5 of benzene in a lot of cases. Now, this state doesn't have a TPH standard, but for remediation purposes, because abiotic and biotic technologies are not selective to specific contaminants, we have to deal with, and we were analyzing and looking for TPH in soil so we can come up with a design that optimizes what we're putting in to remediate the compounds we are interested, specifically benzene, trimethylbenzene, or 1,2,4-TMB, and also naphthalene. So here's the RDC we conducted. Again, it's in firm sand, or fine medium sand. It's pretty firm drilling, and we've got groundwater typically about 5 to 6 feet. We took 21 soil borings. Some of them were on residential properties, so we had access. We had to gain, the client, well, not us, had to gain access to them. We're using the existing monitoring well network. Again, a data point in the subsurface is a data point, continue to use it. But we also installed 10 temporary wells to kind of fill out the plume map that we started to generate by some of this data coming back to us. We also conducted groundwater flow testing. During the initial release, they thought the groundwater was more easterly. There was also some questions, despite this being a fine medium sand, that there was some inconsistent hydraulic conductivity notes in some of the initial well installations and slug testing, so we went back out and re-verified, or in some cases updated that. And as I mentioned a second ago, we're going for BTEX range 124 TMB and also naphthalene here. So here's what we're dealing with. This is post-RDC, so this is all the existing monitoring well network, the temporary wells, the soil samples that we took scattered throughout the plume here, and this is looking just at benzene. So we have groundwater on the left, soil on the right. Now I put this up because in a lot of cases we're given, as injection contractors and practitioners, we're given a lot of groundwater data. Everyone seems to have groundwater data. It's easy to get right, it's relatively cheap, it's easy to collect in the field. But as you can see here, if we'd only looked at groundwater for the site, or we'd done a much more limited soil analysis, soil sampling program here, we would have missed some stuff, like on the west side of the highway. There's some significant concentration in soil. There's also a little lobe here to the southeast where the soil concentrations are higher. So if anybody had approached this with just the groundwater heat map here, right, and using just your groundwater concentrations, we may not have had the correct program and design in place to reach the remedial goals for this site. So we took that data, we then optimized the design, both laterally and vertically in the subsurface. We used that BOSS 200 product I talked about. We did both vertical and angled injections around the roadway, and in the end we ended up putting in 42,700 pounds of that BOSS 200 activated carbon platform, plus the kinetic additives, which include thermal electron acceptors, bacteria, yeast, starch. It's a complete system, right? All that's going in. And we get asked a lot, are you trying to leverage native bacteria? Are you trying to leverage native sulfate, things like that? And I say, while that data is useful to us, we're not going to guess or hope it's there, right? We're going to put in the mixture that we know based on that quantitative data, what we need to get this system moving in the subsurface. So here's what that looks like subdivided. We started with several PRBs here, right, down gradient from the source. The source was up in here. We have one side gradient PRB here just to manage. There was infiltration differences here because of the impervious surface here of the highway. We also did what we called permeable reactive treatment zones on either side of the highway, and then angled drilling stitched, again, on both sides of the highway as well. And then we let it cook for 4 years. And we got lots of groundwater monitoring data. Now, this is the point where I told you earlier we needed soil data, but we're past that point right now for this site. Now we're using groundwater as our basis of evaluation, again, because it's inexpensive to collect, it's relatively inexpensive to run, and you can compile that data very easily to create your monitoring graphs and such. So here's our mass reduction graph for this site. So this is total BTEX plus the trimethylbenzene plus the naphthalene. And the question I get when we show these mass reduction slides and graphs, I get asked what these are, because these peaks are. This is not rebound in the traditional sense, like if you're using other technologies. When you're using an activated carbon-based platform and you're getting soil desorption, you're loading the activated carbon. And in the case of these trap and treat products, they have a treatment mechanism, right? There's bacteria inoculated onto the activated carbon. So this is this cycle, right, of soil desorption, captured by the product, degradation, and that degradation frees up space on the activated carbon to absorb more material. So you're continually disrupting that soil groundwater equilibrium. So we don't see this as rebound in our world, we see this as process regeneration, right? This is transport off of soil. And this is just using one of our wells here, but you could look at this, and these peaks are not as pronounced in some of the tertiary or side gradient wells, right? But you see this is what we want, right? We want to see that the contaminant is being drawn off the soil, using groundwater as a transport mechanism to the product and getting subsequent degradation. So here's one of my favorite animations for any site we've done. You could see us stitching in the initial PRBs, and then the PRTZ on the east side of the highway. And this data was collected real time, then the left side PRBs and the side gradient and angled injections. And then here we go, we're looking at benzene concentrations in groundwater changing over several years. And you can see when we get these blooms and that disappear right from the benzene, again, those are those peaks, that's that transport, again, the soil mass desorption headed onto the product. I missed that last song, I'm sorry if you're keeping track out there. So it continues to go, and I'll skip forward here. I have a summary slide here. So this is what we're dealing with, upper left 1 year, 2 years upper right, subsequently 3 and 4 years post-injection. So we go from percent level, right? We go from DNAPL concentrations in several areas at the site to, at this point now, that says 4.7, but where we are currently with this site, there isn't a single targeted compound that's greater than a single digit. So roughly 5.5 years post-injection here, they're now actually going to figure out what they want to do with the site. Again, there's residential properties involved, so there's multiple layers of this onion they have to work with, and it's also a state highway. So lessons learned from such a program, right? I always caution people when we look at data sets initially, don't focus, like, if something always catches our eye, right? Something's like, ooh, I find that interesting, or ooh, that's a problem, or wow, that's challenging, you know, or how am I going to get access over here? And I always say, you know, take a breath, right? There's still a long way to go once you start that initial dissection of your site, right? That CSM, right? As you start to drill down in it. So don't get caught in a catch-22, right? Don't look at something, right, that seems like that has to be my only answer. That's my only answer at this time. It might be, but let's build some data sets and evaluate it, right? Let's also focus on quantitative data and also using qualitative data to help you get to that point, right? And soil data, right? Soil data is king, right? If you just operate on groundwaters, I showed you in a few of those slides, right? It doesn't matter, right? To some extent, you need to know where your source mass is. Now, there's going to be exceptions, right? If you're doing a PRB, right, there's probably not a lot of soil mass where you're putting that PRB, so you could look at groundwater. But again, these are things that you need to tease out as you go through it. I love qHRSC, right? But again, a tool is a tool, right? That's a remote sensing, you know, so to speak, piece of data, right? It's an invasive tool that gives you an electronic output. And I know that they say they give you corollary samples to kind of help you with that, but again, you still need to take that with a grain of salt, right? Like, it's not, I guess he liked the presentation too. But again, it's still not the hard data that we need. Implement 3D imaging as needed, and again, close data gaps. Don't ignore something, right? Go take that sample if you have access to it, especially if you have a technology provider that you're working with that can get that to you pro bono or at a reduced rate. And then the last piece of this is, you know, these RDCs you do, these qHRSC programs, even your CSM, right? It's a living data set, right? Data ages out, right? I have an email in my inbox right now, 5-year-old groundwater and soil data. Give me an idea of what you can do. Well, I can give you a preliminary idea of what I can do, but we're going to have to go out and look at it again, right? Data ages out. So again, use tools and technologies to update it, optimize your site, and hopefully you get to the result that you expect. I just want to briefly acknowledge my co-author on this, Gary Simpson, who's been with AST over 30 years. He's retiring. This is his last year with us, but he's been a great mentor to me and a lot of others at my company. So with that, I thank you again. Thank you to my panel. Thank you, Fayaz. Thank you, Gene.
I might as well ask, what was the cost?
It's actually, Gary knows that number. I would say we're doing a similar site like this right now in North Carolina. Actually, I can tell you that the qHRSC for this site was about $40,000. And that includes the probe, the HRSC company, that included all the soil samples. There was some soft dig involved for several of those. But the way we looked at it is upfront spending $30,000 to $40,000 for that program. We ended up reducing the overall initial cost of this site by about 25%. So you spend a little upfront to remove hopefully a lot more on the back end. So And there's a lot of documents that I'll talk about this. There's an ITRC document that was published, I think, in 2020 that talks about the benefit of spending additional upfront to get you not just time, but also cost down as well. And they've got a nice graph. I've actually used it in some of my presentations that is trying to encourage us as practitioners to do that a little bit more and say, more data up front is going to save me time and money on the back end. That's everyone's question though, right? How much does it cost?
Hey, Derek, I have 2 questions. The first is, what happened to the accident release? Why there were 2, like, source areas?
So the spill occurred on the west side of the highway. We were not allowed to drill. We had access to the right-of-way, but we were not allowed to go in the highway. So you have a shadow there, right? So what looked like 2 source areas is almost surely one. And that's part of the reason that we attacked it with angle injections as well, because we couldn't, it's like at a gas station site, you have your pump islands, that's a shadow. Buildings, they create the shadow. So that's probably very similar concentrations across it, but we just weren't able to go in invasively, vertically, and go look at it. So we attacked it we snugged up injections under the highway.
Okay, understand. The second question is about the gypsum injection. Was that the targeting for sulfate-inducing bioremediation?
So yes, so we include with the activated carbon platform, which has the bacteria inoculated with it, we add to the batch tank based upon the stoichiometric design, either solely or a mixture of gypsum for long-term release sulfate, or also magnesium sulfate for immediate soluble sulfate. And then again, there's also yeast and starch in there, but you're creating this optimal microbial mix for the microbes that are on the carbon to continue to function, not just in the short term, but the long term.
Thank you.
Thank you.
Derek, at what angles were you able to drill under the road?
So we've developed a foot for a standard 7822 geoprobe. We're really maxed out on the layback at about 25 degrees. So you will have some setback. There's still, if you were to go, probably drill immediately under the road, depending on how that release migrated. Again, we don't know. But there's probably some residual there that we can't get to. However, because you've covered the whole area, especially that's groundwater, within the groundwater column with the product, that any additional release or bleed out would be managed by the activated carbon. That's a good question.
I have one. Derek, so the heat maps that you showed for groundwater in the soil heat map, was it like saturated soils or is it like Vadose zone soils?
It's a good question. So the soil heat map was all saturated soil. The product you saw selected here is not for the Vadose zone, it's for phreatic zone remediation. So if we don't have groundwater, we can't get transport. If we can't get transport, we can't get remediation. So it's a great question. I will say all the maps you saw from the animations and so forth, that is quantitative data. None of that was qHRSC data at that point. So that was actually physical soil and groundwater samples to build those maps.
Okay. Yeah, and then continuing on Ziki's question about sulfate reducing conditions. So maybe you didn't show the data because you didn't have the time, but were able to show sulfate reducing conditions with measurements of ORP and sulfide, etc.?
Yep, so the best way to monitor these type of reactants is to use groundwater, look at your sulfate concentrations, nitrate, nitrite, which are probably going to get consumed first by your consortium of bacteria, methane, carbon dioxide. There's a bunch of parameters that are really easy to monitor both up front and afterwards.
Okay.
Is that FOS 200?
It is approved in Florida. Yeah.
Okay, any other questions? No?
Thank you.
Okay, thank you, Derek. Okay, well, thank you all for hanging around here, and this is going to be our last talk. It's going to be on a DNAPL remediation, examining the life cycle of solvent site. I'm kind of intrigued to see what Jim Langenbach has to say about this over here. So, Jim, take it away.
Thank you. I guess I'll be competing against WrestleMania next door. And I get through this so then everybody can get lunch. I'm sure everybody's looking forward to that at this point. So I'm going to be talking about a site that I've literally been working on for almost 30 years. If you'd asked me 30 years ago if a site ever lasts that long, I would have been like, nah, these things clean up quick. But now I realize that 30 years actually is not that long in the life cycle of some of these large chlorinated solvent sites. So the site I'm going to be talking about is located in Central Florida. It's a precision fabricating and cleaning site. It's in Cocoa. It was a metal fabricating and maintenance facility. It still is. TCE was used at the site for metal and parts cleaning from 1964 when it opened to 1977. They did have a couple documented releases, one in 1966, which is an important year to remember, before I was born, so the site predates me. It was a drum release, a couple 55-gallon drums, and in the mid-70s there was a rail car release. And then, of course, over time, there were some incidental spills from cleaning operations. Interesting about this site, you're not going to see this too often. This is data of peak TCE concentrations detected in private irrigation wells, 1966 to 68. So it's one of the earliest documented laboratory analytical results associated with health department collected data in the United States, actually. This is one of the reasons that some of the researchers that I'll be talking to that have worked on this site were so interested in this site because of this very early analytical data associated with this. But there was detections of, you can see here, of over 110,000 of TCE in October 1966. It's about 2,000 feet down gradient from the PFC site, or PFC plant property. PFC began their operations in September 1964. The first documented release at PFC was in 1966. Groundwater flow out here, the maximum groundwater flow is about 1/2 foot per day, and it's sort of east, slightly northeast towards the Indian River. Assuming there was a spill on the eastern fence line of their property on day one of operations, not when they documented the drum spills, but on day one of operations, the maximum travel distance at the maximum groundwater flow velocity is about 180 feet per year, so 360 feet. But yet you've got 110,000 that they're being told they're responsible for over 2,000 feet down gradient. So this kind of started the process of this site. There was a lot of work that went into this site, even before my involvement in the mid-90s, with the Department of Health, the DEP, sampling of irrigation wells, installation of monitoring wells, soil borings, you name it. A lot of different phases of activity, risk assessments that were done by DEP and EPA. Then in the mid-90s, 1996, there was some, the site was headed towards litigation and some significant, potential remedial actions that PFC was going to be responsible for, because they were basically being identified as the responsible party from the plant all the way to the Indian River Lagoon. So this is where you'll see, and I'll get into this a little further here, but a lot of work that went in beginning in the late 1996, 1997 timeframe with the implementation of Waterloo profilers, bundle wells, transect high-resolution site characterization, and a lot of just the data collection to sort of prove a litigation case. But that data collection and the work that was done, we're talking about Waterloo profiler data collection with collection of thousands of groundwater samples. This is sort of was unheard of at the time that this was being done. So when you think about a site like this, what would have typically been, especially in the mid to late 1990s, the typical path or typical conventional assessment approach? You would have gone out there, you put in some conventional monitoring wells, you're focused on big picture delineation. What's the overall dissolved plume? And when you do that at a site like this, what's the result? Well, it's a single plume. It's a single plume that you draw a big circle from the plant and it goes all the way to the Indian River Lagoon. And the little inset map is actually a 1986 DEP map of their conceptual site model, which basically pinned the entire contribution of contamination from PFC all the way to the Indian River Lagoon associated with PFC, even though you've got wells 2,000 feet down gradient that had over 100,000 of TCE in them in 1966. And keeping in mind that, just so you recognize, this area is in the aerospace sort of capital of Florida. Everybody in the mid-60s had access that worked at the Space Center, at the Air Force Base, at various establishments in the area, aerospace industry. They used chlorinated solvents by the tanker load. A lot of workers back in the mid-1960s, they did all their own engine cleaning, their own mechanical work, and if you drive through the neighborhoods east of the site, you'd see a lot of that back in the day, and even going into the 90s, where there was a lot of that sort of, I'll just call it blue collar, machine shops in the backyard, people pulling engines out of their cars. So there was a lot of incidental use of chlorinated solvents in the area just because of the availability of a super solvent for degreasing. But when you look at this site from the conventional assessment approach, you realize you do really have a very weak conceptual site model. And then that whole question about what about those 1966 Department of Health results? So this is sort of when the late 90s, 1996, 97, when Dr. John Cherry and Dr. Beth Parker, they were at the University of Waterloo at the time, currently at the University of Guelph, when their involvement became with this site. And this is kind of when I got involved at this site as well, as basically a young staff engineer, learning how to, collect data and evaluate, conceptual site models, even though that term didn't exist at the time. What we looked at with this site was using a transect-based approach. So basically, you got groundwater flow essentially almost due east, doing transect cross-sectional slices through the plume as you move down gradient to get a high-resolution understanding of what actually was occurring within the subsurface. To do this, there was some development and testing of some of the industry tools that we are using today, that actually the development and testing occurred at this site. So you may have heard of the Waterloo Profiler. So that was one of the first profiling tools for collecting discrete interval groundwater samples using push rig technology. Bundle wells, we were putting in bundle wells that at the time were a massive tubing with little sample ports on them, and we'd have 12 or 15 tubes that would go down a DPT rig. Well, that ultimately became the Solinist multi-level well sampling system that eventually evolved out of the bundle well technology that was being developed at this site. The results of all that characterization that was done in the mid to late 90s there was documented in an origin and characteristics multi-sources of TCE, DCE impacts to the superficial aquifer study. And that led to remedial measures that were ultimately agreed to following a settlement of the lawsuit of the United States of America versus PFC as a civil action lawsuit. It was a highly contested litigation, 5 days of mediation, and the outcome of that was a consent decree that became effective February of 2002. Some of the key settlement outcomes, and then I'll kind of jump back into what some of the transects and characterization looked like associated with that settlement. But some of the key assessment activities were 6 transects perpendicular to groundwater flow. As I mentioned, extensive groundwater profiling, soil borings with high interval saturated soil sampling. And then some of the key settlement elements were basically a determination that the VOC impacts from the plant PFC was only responsible for chlorinated solvents from the plant to US1. Everything east of US1 was not associated with a release from the PFC plant. So when it came to doing active remediation east of US1, they didn't have to deal with. As part of the settlement was a remedial measures plan, basically equivalent of a RAP, that described pump and treat and M&A for the PFC plume swath, which was a legally defined, this is the limits, this is the footprint that within this, the plume resides. There was a requirement for a ISCO pilot test and then some monitoring associated that was required, and as well as notification requirements, which are still in place today, where everybody within the notice area gets with legal mailings, just sort of almost what we have to do with 62780 now. Just a real quick snapshot, just to give you an understanding, sort of some of the magnitude. This is just running along the property line. And I'll be talking about transects as we go forward here. So this is the fence line transect, and you can see along that transect there is various bundle wells installed, as well as profiler locations, so Waterloo profilers. And keep in mind that each of those dots you're collecting, 10 or more groundwater samples. That's something that we weren't doing much of in the mid to late 90s. So here's kind of the assessment approach. You've got go back. There we go. Transects along right-of-ways of the roads, going up towards the property itself, the plant. And then here's just a typical illustration of a bundle well. So basically a multi-sample port system that's put in the subsurface to collect data at multiple depth intervals. So as part of this, you start thinking about it, how are we using this data that we were collecting? We're using it also to infer DNAPL zones based upon the transect data. So we have transect line at the fence line, but using that transect data, high cross-sectional slice of what the plume looked like, you can project back from that and actually infer and identify where your likely DNAPL source zones were, and then go in and do sampling within those DNAPL source zones to actually look for that zorbed mass or that DNAPL type information. So early on, in the 60s, we know that was the early stage release time for this site. The release occurred in the mid 60s. When I got involved in this site, we're already at sort of I'll call it the middle stage in the DNAPL site life cycle, where you're not finding DNAPL as pooled DNAPL. The DNAPL is largely zorbed and diffused into the matrix at this point. It's primarily a sand aquifer, but there is some clay stringers, clay seams. There's actually, we had one location where we actually had actual DNAPL, positive DNAPL based on Sudan for testing, shake test. But that was the only sort of wild DNAPL ever found at the site, even though we have very high concentrations zorbed and diffused into the matrix, sort of at this middle stage in the DNAPL site life cycle. So here's kind of looking at some of the just quick snapshot of the transects. So this is the fence line transect. So, kind of running north to south on the property line. You can see some, all the dots essentially represent sampling locations and concentrations based on percent solubility. So your darkest concentration, 10% solubility, that's over 100,000 microgram per liter, and 10,000 stepping out from there. But this was sort of the first time, in the late 90s, this was sort of unheard of. The people were used to just seeing footprint of a plume map based upon some dots and a circle. So this was kind of a very unique approach in the mid to late 90s. This is the West Ridgewood Drive transect moving east. Just a quick snapshot example of that one. I think I got one more transect. Oak Hill transect moving east. So as you're moving east, you see the concentrations dropping, but you still see actually these core locations of high concentration mass. It's typically diffused or associated with these fine grain units, and you actually would have locations. I remember, at the time doing the sampling and being amazed to see concentration variations on the order of 3 and 4 orders of magnitude over the course of a foot to 18 inches. So we see the significant concentration variability within a transect of a cross-section of a plume like this. This is just an illustration. This is sort of that plume swath notice area. So this is the area that gets noticed, along with its dispersion effect boundaries based upon modeling that was done by University of Waterloo. And again, PFC is technically responsible for about halfway, but the settlement included this entire notice area. And then just showing here, these are other chlorinated solvent detections that are just out here within the neighborhood areas that are not associated with the site. get into the remediation. So when we think about what was conventional remediation in the 80s and 90s, a lot of times it was just conventional hydraulic capture. You know, you've got a picture of a plume, you put extraction wells throughout that plume, you provide hydraulic capture, you start pumping, and all's gonna be good. You screen the extraction wells based upon the overall vertical distribution of the plume. You really didn't think too much about, you know, silt and clay, little, you know, 2-inch thick silt and clay layers. You just blew through that and put in extraction wells. Typically, your treated effluent from a system like this, where would you put it? All the state guidance, all the state requirements required. Typically, you'd put it up gradient of the plume or off to the side. You would never put it back within a plume. But that was, you know, that was sort of the way it was done then. So what does that do is it creates this big stagnation zones. And it also eliminates an opportunities for some enhanced flushing that you can get by putting water back within a plume itself. And a lot of times when we did designs back in the late 80s, 90s, we didn't really have a clear exit strategy. The exit strategy was put in a pump and treat system or remediation technology and operate it until you reach cleanup standards, right? There wasn't a mechanism out. But what was done at this site was a little different. The extraction well system wasn't put on basically the overall property or the area PFC was responsible for, say all the way down to US 1. It was focused very much specifically on the plant property. And the treated effluent was used, and it was installed with extraction wells specifically screened above the clay layers and below the clay layers, and then an injection well network down gradient on the fence line of the PFC property that pushed in the water above the clay and above the clay at the same ratios, creating essentially a hydraulic barrier and then a hydraulic capture zone on the plant property itself. This is just a typical actual groundwater capture map based upon the potentiometric measurements collected during many years of groundwater system operations. So very different, took quite a bit of regulatory back and forth to get this type of system approved ultimately to be installed at the site. And then monitor natural attenuation for the down gradient plume. So from the fence line all the way to US 1, monitor natural attenuation. So here's basically the implementation. You've got a network of recovery wells, injection wells. It originally designed to operate at about 38 gallons a minute, and then carbon polishing and treatment. You're basically extracting contaminated water, putting back clean water along the property boundary. Did lots of optimization strategies during this, modified pumping configurations. Our original design didn't include extraction wells, which were as deep as they were put in. They were put into 80 feet. We had actually designed them much shallower. We were forced by the agencies to put in deeper extraction wells. We ultimately went back in and abandoned the bottom 25 foot of those extraction wells, and we saw significant improvements to our extraction system operations. We optimized mass extraction rates based upon changes to our pumping. We turned off certain wells. We added certain wells in terms of enhanced pumping. We also went ahead in 2015, did an initial bio area where we did some bioremediation and used the extraction system as a pulling mechanism to move that within the subsurface. You can see really quick the results there. We had concentrations at over 3,000. They quickly dropped when we did that, and then we did another round in 2019 to sort of finish it off, and ultimately completely shut down the system at that point in time. Just a quick shot of the 2019 phase of bio. The 2019 phase of bioremediation, in addition to doing some locations on the plant, we did a few locations along the transects where you'll see, and I show you some of the concentration data where we were still having some lingering back diffusion related, low-level concentrations to sort of work to polish that area. Lots of optimization. This is again just speaking to all the different optimization steps. And what the interesting thing you'll see is when you optimize You'd see our TCE concentrations go down, we'd optimize, and we'd get a bump. See the concentrations go down, make additional steps. So we were continuing, every time we saw concentrations go down, we would do what we could to optimize. And then of course you see what happens when we implemented the bio as a sort of a polishing phase in here. The concentrations really drop. But the average concentrations are kind of running right in this realm. And just think, if you didn't do any type of optimization, the system would have continued just running at a very low loading rate and removed a heck of a lot less mass over time than it did using the various phases of optimization. This is just mass removal over time. And you can see, again, the concept of constantly making adjustments to optimize and remove and enhance mass reduction. And then we went to bioremediation down at the end here as polishing. You can see essentially the mass flux or mass removal rate essentially dropped to 0. Jumping in and looking at some of the concentrations versus time. So what happened as we started flushing and moving groundwater, extracting and then re-injecting at the property line. This is the West Ridgewood transect. So one of the first transect east of the PFC plant property line. You can see very high concentrations initially, and then they slowly tail off with time. And then you can see this is an inset map because there's so much the data down here. We go to bioremediation here, polishing. You see a little blip. That's desorption from enhanced back diffusion and essentially going to non-detects. Here's drilling in at a couple of the wells on the West Ridgewood. You can see concentrations very high, 70,000s going down, essentially cleans. This is an interesting location because it's showing, well, some of these locations went clean very quickly. Like this location took a lot longer to clean up over time, and that's a direct result of back diffusion. You're putting clean water past that's moving down gradient over it, but there's a lot of mass in that location that was diffused into the fine-grained sediments, and that was mass diffusing at an enhanced gradient out of the matrix into the water and then attenuating over time. So you see that clearly on this, and that was matched up with bundle well data and other data that had been collected to kind of verify that. Oak Hill, similar results, significant concentration changes over time. US Highway 1 transect, same thing. Of course, lower concentrations that we're starting with, 1,000 and a few hundred, but then, tailing down over time. And where are we today? So April 2024 results, and it was actually the site was just sampled last week or 2 weeks ago. In April, we sampled 21 wells. 14 of the wells are less than GCTLs. 7 of the wells had concentrations greater than the GCTL. The only exceedances are for vinyl chloride. 1 of those wells has VC above 10 microgram per liter at 16, and then the other 6 wells, the remaining concentrations are at less than 5 microgram per liter. So this is a site that had hundreds of thousands of microgram per liter. This is over a 2,000 foot long, almost 2,000 feet down the US 1. So it's a pretty good sized plume. When you look at a little map, it doesn't kind of show the dimensions of it, but some significant reductions over time. So kind of looking at this site from sort of that 30-year perspective, I think it's one of the few things to point out. It's really important to understand where your site is in the DNAPL life cycle, right? Is it an early, mid, or late stage type site, first of all, when you get involved with it? Early stage, did the DNAPL release just occur? Is there actual recoverable DNAPL? Has it made it into the matrix? That's what you're going to see in the mid stage. The mid stage, you're going to see, high concentrations and maybe a pretty robust groundwater plume, but you've got a lot of that mass. It may be not as recoverable DNAPL anymore, but it's diffused and absorbed into the matrix. And then you get into the late stage. That late stage is, the DNAPL is essentially depleted, but what you're getting is, that remnant back diffusion occurring as the plume is very slowly exhausting itself. As remediation professionals, I just encourage everybody to think outside the box, customize your solution, and be persistent. There's a lot of things that were done at this site that didn't follow the normal convention of the time, whether it be extraction well, screen lengths, where we were re-injecting clean water, transitions that we did, optimization steps that we did, that a lot of times we are at odds with the agencies on some of these steps, but we're persistent and kept pushing. And when we were given finally the green light to do it, boom, we'd have success with it. So it was kind of like, just be persistent. Don't let no stop you, just keep asking. For complex sites, a lot of times during remedy implementation, it's just another phase of site characterization. It's not a linear approach. You don't start an assessment and then begin a remediation. It's just linear, and you're heading for the exit. It's something that you're revisiting your conceptual site model. You're looking at it. You're optimizing. I know a few of the other presenters have talked about use the word optimization. It is absolutely critical, because the chances that you go out to a site and know it perfectly and have it completely characterized and go in and your remedy works 100% perfectly, it's not going to happen. You're going to learn things as you go and adapt to that and make changes. And then just the last thought is, that sources really begin to reveal themselves as the remedy progresses. So I kind of look at it as sort of clearing the smoke. The dissolved plume is the smoke. You start clearing things away, it really helps you identify where the source is. And I just wanted to point out again some of the PFC contributions to industry associated with this site. There's been multiple master and Ph.D. students that have earned their degrees through University of Waterloo and the University of Guelph through the research at this site. This is essentially one of the first sites where high-resolution site characterization really came to bear before the term high-resolution site characterization ever existed. We saw the development and testing of various tools that are being used in our industry nowadays, and multiple proceedings and published papers that have come out of this site on back-diffusion modeling, and other combined bioremedy approaches and other just information that's contributed to industry. And I just wanted to acknowledge the late Jack Shy, who PFC, who really pushed for and encouraged a lot of the research on his site over time. Dr. Beth Parker, John Cherry, Steve Chapman, and Bill Pence with Baker Hostetler, environmental attorney that represents PFC. With that, I'll take any questions. Or we can go to lunch.
I have a question. What happened to the plume on the other side of US 1?
The plume on the other side of US 1, that's an interesting question. So the settlement required us to sample up to 8 wells annually for 20 years, as selected by the agencies. We sampled those wells. The concentrations, some of them they're sort of just sticking around where they were, which is another indicator that there's other sources out in that area that are not associated with this site. Because the site wells within the plume swath west of US 1 have essentially all gone down to single digit or less vinyl chloride, whereas east of US 1 you still have a lot lower, but they're probably NADC type concentrations that are out there. And different degradation ratios of contaminants.
Excellent presentation, Jim. I just have one question. Well, a comment, I guess. I like the way you walked us through the various stages of the life cycle and what tools and approaches were used at each stage and to get to the end point. One question I had was, you talked about 30 years, but when did you first start doing the remediation, and how long have you been remediating the site?
So, so my first involvement was in '96. The pump and treat system that was ultimately designed and installed started operation in it was June or July of 2002, and it operated till 2019. In 2015, there was a period of several months where it was shut down when we implemented bio, because we were doing a flushing approach and didn't want to just be pulling our electron donor out. So there was some intermittent operations for the 2015 to 2019 period. I will say from the 2003, from the whole time this system operated, this was not a gravy train project where we were like, we get to do O&M on a pump and treat system for the next 20 years. No, the personnel at the plant had 40-hour OSHA training, 8-hour refreshers. They were taught how to operate the hydraulic capture system, pump and treat system. The plant, you know, there were a bunch of, you know, they're the type of people that, you know, they ran the system. It was just part of their they just had a system. They ran it. So, and our involvement was essentially, you know, helping with sampling twice a year and writing reports. So it kept the costs. For them, it was actually the most cost-effective way to do it, because we had looked at doing a large-scale chemox and to do a chemox at the site, which wouldn't have been the appropriate technology at the time anyway. But we were forced to do a pilot, which demonstrated that it wasn't going to work because of the rebound that we got. But the scale-up costs were significantly higher than them just operating as facility operators, running a simple pump and treat system that they ran.
Okay. Any other questions? No? Okay. Well, let's put our hands together once more for all the presenters. And thank you all for attending and on your engagement in the whole process. Enjoy lunch, and hope to see you guys back again for the afternoon sessions. Thank you.
Just a quick housekeeping comment. There's multiple groups doing events and serving lunch, as you can tell. We have Havana Nights on the left. Don't go there. I think they are serving crack cocaine on the right. Definitely do not go there. Our lunch is served in a room behind my back. So as you leave the room, make a left, another left, get your ticket ready, and enjoy your lunch. Thank you.